All right. Good afternoon, everyone. I think we had an introduction only on this unit so far. So today we will look at some of the details on software engineering. Okay. So if you notice in this module, we are looking at the mechanisms and some of the best practices when it comes to engineering a product. Yes. So you see the word engineering here. We'll also emphasize that because it's not just building something. There are a lot of things we need to do in a methodical manner to get to our final product, right? We'll be looking at software engineering principles. We're also looking at certain mechanisms in getting things done. We also look at some of the established code, sample code and things like that. All right. So let's get down to the details. Okay, now before I speak about the details, now here's a very interesting chart. This is a chart done by Standish Research, Standish Group. Yeah? So what they've done is they've looked at projects from 1995 to 2009 to see what is going on. Right now, this is important because we can learn a lot about what happened to our project starting from almost 1950s, because that's when the computers became business oriented or corporate level kind of thing. So before that, we were all building military and government related projects, right? It came to mainstream in the after the World War II, 1950s and 60s and things like that. So if you look at projects, right? Now look at the yellow line. Yellow line is growing, right? And in the first set where it is successful, in 1995, you have about 15 successful and about 30 something in 2009 successful, right? Whereas challenged and cancelled. Now, if you look at the challenge means maybe it took a long time, longer than the actual time, or it spent more time than the actual budget. So that's what is called challenge. Now, in 2095, there were massive amount challenge, more than 50. And more than 40 was 2009 challenged, right? And if you look at the cancelled projects, we also have a significant amount in 1995. A lot of projects were cancelled, 30 something. And in 2009, the cancellation is close there, but it's reduced. Okay. Now, what can we learn here? You can see we have improved the engineering principles. Through that, we were able to have many projects successful and less challenge or cancelled. So what we learn here is that we have improved our software engineering method, isn't it? That is why by 2009, we were able to have more successful project than challenge and cancel, isn't it? If you go forward to look at the past as to how people have used software engineering projects, right? There was a famous saying in 1950s. This is called the Mongolian hordes approach. Horde mean අපි කියන්නේ සිංහලෙන් හරක් රැලක් කියලා හරක් ගාල කියලා අපි කියන සිංහලෙන්, right? So Mongolian horde mean in Mongolia you have a huge amount of cattle, right? So in the 1950s, what they thought was if you can put more people, the project will somehow come out. That's what they thought. Like programmers la ඕන තරම් දාගෙන යනවා කොහෙන් හරි කොහොම හරි project එක ඉවර වෙනවා. අපි දන්නේ නැහැ කොහොමද වෙන්නේ කියලා. Somehow it will get completed. So but yeah, it might get completed, but the completed code will be full of defects. It will work today, it will break tomorrow, right? Some parts will work now, some part will break later. So then we will be again coding to fix those bugs. So there is no end date for the project, right? And because there is no proper designing or architecture level questions, nothing, you keep on coding as you think about the problem. So this is called the Mongolian hordes approach. Not a very good approach at all. This means put more people, it will someday it will be completed. That will never happen, right? But in the 1960s, when it comes to rockets and various space projects came in, and also there were a lot of other projects, other software systems came for the military systems like jet fighters. There are programming happening. Rockets, there are programming happening. Planes, there are programming. So these are very complex and very expensive affairs. So that's when people identified the software development as a crisis, right? Because you need people who know electronics in order to program at that time. If you are not an electronic engineer, you can't be a programmer because there is no computer science as such, right? So in the 60s, after having multiple meetings around the world, then came the software engineering discipline. Before that, there was civil engineering, electronic engineering, right? So things like that. Now the new term came software engineering. And this became very important in the late 90s because the programmers who did the programming in the 50s and 60s, I think it's because the memory was expensive. They were using two memory location to store the year. So if the year is 1999, you only store the 99, not the 19, because 19 is common for all the other years. But there was a day, right? When the year 2000 comes, you go back to 00, not 2000. So that was called the Y2K bug. And the whole world was going through a massive confusion because they thought everything is going to stop. Right? I've shared some video on the LMS. You can have a look at it. What happened? Okay. So this is all because programmers didn't have a way of building reliable software. Right? So there was no software engineering practice as such. So what is software engineering then? This is just like any other engineering. It is a method to design, develop, and test software to the customer's need. Just like building a bridge, you're building a bridge, you're testing the bridge according to what the customer wanted. Or let's say you're building a house. In the house, there's nothing much to test, but there is a specification that you're getting from the client. So for that, you are building the software. Now, second point is software is engineered. What does that mean? So software is properly designed, properly developed, properly tested. So three things: designed, developed, and tested according to the engineering principles. So it's not just the software engineering we are talking about. We are talking about the general engineering principles. Okay. And just like a bridge or a house, we also bring in other things like quality control, safety measures. They are all properly addressed. Okay. Now, how do we know whether these things are going according to the plan? Now, we need statistical evidence. Say, for example, we have 100 things. Out of the 100 things, how many things are properly working? Is it 50 things, 80 things, whatever? So mathematics is employed here in different ways to understand whether we are on track, right? How many bugs are there? How many features are there? Out of that, how many are working? How many are not working? So things like that. So in order to get there, we also use something called the peer reviews. So peer is a person working in your department or in your organization or whatever. So someone working closely, right? Part of the team, right? So maybe it's a QA department, maybe it's a testing department, anything. So you work with a big team, right? So peer review is you have other peers, other people who are also working with you, maybe testing, maybe writing documentation. So, things like that. And there is also project management principles coming from, let's say, construction industry. So in project management, there are three things. There is time, there are actions, and then there are resources. So we are trying to manage these three. That's what project management is all about. There is time, there are resources, and there are actions, what to do and how to, what to do with what we are doing, and then what is the deadline. So you bring the project management principle also to software engineering. Okay. Now, after everything is done, after software is completed, build everything, then the next project is, okay, how do you maintain this software? Right? Because you don't just build and go away. Okay, you can, but most of the time you also need to give after sales support. Maybe some upgrades are there, maybe some new change requirement coming in. So how do you do that? So when you say software engineering, we are basically talking all that, right? Design, develop, testing, and then looking at quality and safety, and also looking at peer reviews, and also looking at whether we use the project management skills there, and also what is the maintenance process. So these are the main sort of areas we take under software engineering. Now, here is another point here, right? It says it should be evident from the requirements what is and what is not required. What does that mean? That means your requirement will be very, very clear. So you have to, generally the requirements are coming from the customer, but that doesn't come directly to the software developers or the engineers. Generally, those requirements are captured first by the marketing department, and then by the BA, business analyst department. And then they only translate that to us, the programmers. So you might not get direct from the client. So if you don't understand something, you have to directly get it from the source, that is from the client. So when you understand the requirement, then you know what to do and what not to do. Okay, what is required and what is not required. And the only way to find out is from the requirements. Right. Now we looked at what is software engineering. So now who is a software engineer then? Okay, who is the person? A software engineer is an educated person who has gone through the engineering principles, right? So this person has used scientific principles to their work. And mathematics is a very big part playing here. I told you, right? Why? Because we look at things from a statistical point of view. How many bugs, how many features, how many working, how many not working. So things like that. And also there may be other calculations required in your algorithm. So that is also area where you will need mathematics. Okay. And the software engineer need education on specification, design, turning design into programs, and then software inspection and also testing. So an engineer requires all these skills, isn't it? How to understand, how to develop a specification, how to design something, how to turn the design into programs, that is how to do the coding, and also inspection of the software and also testing. So the whole point of software engineer is to convert a requirement into working piece of software, which is, we say, fit for purpose, right? So the objective of the software engineer is to come out with software that is fit for purpose. So what is fit? What is purpose? Well, that comes from the client. And then if you look at software development companies, who are they? What are they doing? Right? If you look at many software companies, they spend heavily on training, and that is why they hire software engineering degree holders. Why is that? Because they know these students who come from software engineering degrees have gone through the basic fundamental engineering principles, and they also have a mathematical background. Yeah. So that's why it is important to come up with the right education. And if you look at the rest of it, like say project management, software design development, software testing, and also service management. Service management is after sales. How do you manage the service? The fact that employees are professionally qualified increases the confidence in the ability of the company to deliver high quality products and services. So they don't need to give you a degree because you are coming with the degree discipline. But then they can train you on what is required for that particular company, isn't it? And let's say you learn Java principles and data structures and everything in the university. And when you go and join a company, they may be building, let's say, stock exchange software or an accounting software with Java. Maybe you don't know what is an accounting software in Java, but that training they can give you. That's called domain knowledge. So then you will learn, okay, what is an accounting package, how accounting packages work. And later you will realize, okay, how can I map the accounting knowledge domain into my Java programming knowledge? For example, what is the most suitable data structure to store the invoices, right? Should I use a stack? Should I use a queue? Should I use a vector? What should I use? So that's why you're applying the knowledge you gain in your university into the real world problem solving, right? So you see, now if you don't have that previous knowledge, you can't build a good product. You are not a useful person to the organization, isn't it? Right? Now, here's another very interesting concept from Babylonia, long time ago, right? Thousands of years ago. So they had a concept called accountability. What is that? In fact, they had a name, Hammurabi Code. So they have a concept called the Hammurabi Code, which is to do with accountability. Accountability is who is responsible, right? Now, look at the second part. It says it included a law that stated that if a house collapsed and killed the owner, the builder of the house would be executed. That means if I go and build a house and for something happened and the house collapsed and people in that house died, then the government can kill me. I will be executed. Right? So that is accountability. I built the house not properly and they died. So they can kill me. Imagine if we do that for our products these days, many people will be dying. Right? So we don't have it luckily, but somebody has to take the responsibility. So is it the organization? Is it the software company that is taking the responsibility? Or is it the software engineer taking the responsibility? Right. So if you look at the challenges in software engineering, what are some of the challenges software engineers are having? Right? Number one is delivering high quality software on time and on budget to customers. High quality, on time, and on budget. Three very important things. Now, you can do, provided you master this skill very well. Okay. Now, going back to that Standish Group report, this is from 1999, by the way, right? 33% of the projects are between 21 and 50% overestimated, right? So 33%, almost 1/3 are overestimated. What do you mean by overestimation? Overestimation can come in two ways. One is time. So for example, the team says we will build this project in 1 month, but they take 2 months, not less, right? Very rarely they take less. So, or they'll say, right, this project will cost 1 million rupees, but at the end it will be costing 2 million rupees, right? So something like that. So these are the numbers. So it's a 18% are between 51 to 100 overestimated. And then 11% of the projects are between 101 to 200% overestimated. So that's staggering number, isn't it? So if you look at 11% of the projects are 200% overestimated. 33% projects are 50% overestimated. So that's a huge number, right? So estimation is another actually art. It's very difficult to do, but you will notice when you do things like agile, you will be able to perfect your estimation, right? So here's another one. Actually, the same thing in a graphical form. Yeah. So this is under 20%. Actually, 20% overestimation is about 35. 21 to 51 overestimation is around 30 something, right? Less than 200, actually more than 200, sorry. Estimation is still there, right? It's about maybe 2.5 something out of all the projects, right? So there are projects that are overestimating 200%. So like you charge 100,000 for the project, but your cost is 200,000. So you just lost 100,000 to the organization. So estimation has to be very accurate on one side, and then on the other side, your software building process must be optimized so that you can reduce the cost. Okay. Now, in order to reduce the cost of software engineering and increase the efficiency, what are the assets an organization should have? These are called the software process assets, right? Number one, a software development policy is required. These are things that we discussed today in a conceptual form, but as you move forward, we will see how we can build it. Or I will share you some of the chapters which you need to read from the textbook. All right, so I won't be duplicating what is in the book here in the presentation. So you need to go and read that. I will mention which chapter, which book to read. And then number two, process maps that describe the flow of activities. So any new person coming to the organization must know, all right, this is our process. This is where we are starting. This is what we're going to the next and the next and the next and the next, right? And then procedures and guidelines that describe the process in more details. So you have the basic flow and then the detailed flow. Then we have checklists to assist with the performance of the process. Checklist to assist with the performance of the process. So are we doing it right? So we might have a beautiful process, but is it working? Right. So that's the next thing. That's called a checklist. And then we have templates for the performance of specific activities. Do you have sample documents? Because the newcomers coming to the organization, you tell them, okay, give me a SRS. They don't know what to do maybe. They might bring in what they learned in the university, but the office might have a different format. So we need to have a set of templates where we can give it to them saying, okay, here's a SRS template, use this. Or here's the a bug report template, use this. All right. And then loads of training material to the employees. So these are the things we need in any organization. We call it the toolkit, right? A toolkit for the software engineers. And then high quality software development processes. What are some of the processes we can use in let's say organizations, right? So here's a list of things: project management process, requirement process, design process. These are processes. So if the organization doesn't have any of this, they must develop these processes. Otherwise, you are going to face serious problems in the very near future. Coding process, peer review, testing, supply selection and management, configuration management, audit process, measurement. improvement, and also customer support. So this should be transparent and this should be available for everyone in the organization. Right. Now with that in the background, so let's look at what are some of the methods available when it comes to building software. Right. These are some of the famous ones. There may be others also. There are things like extreme programming and all that, but these are the sort of the most famous ones. Okay. First is pretty old. It's called the waterfall model. So in this model, we have multiple steps. So you have step one, you do something, and then after that, you go to step number two. After that, you go to step number three. After that, you go to step number. So you go step by step. That's why we call it waterfall. Like a waterfall, it falls from one to another, right? And so there are a few others. We will take each one and see what it means. So the waterfall model employed for projects where the requirement can be identified early in the project life cycle or known in advance. So if you know the project details in advance, you can use that, right? In fact, if you look at the chart here, it's called the V chart. On the left, we have studying of the system. On the right, we have the developing of the system, right? So we have requirement gathering, specification development, designing, and then coding. The right-hand side, we have the unit testing, integration testing, system testing, and also acceptance testing. Okay, so as it says, V is requirement, spec, design, and coding. Right is testing, system development, and accepting. So each phase has an entry and exit criteria that must be satisfied before the next phase commences. So what does that mean? You can't start the specification phase without finishing the requirement phase. And also you can't say specification phase is over without doing certain things, right? That is the output of that. So only when input and output are satisfied, you can say this box is complete, right? Next is called the spiral model. What does that mean? Now this started in a later stage in 1980s, developed by Berry, right? So it's a reusable prototype. Now the spiral is like this. It's a spiral. Yeah. So here what they say is software development is not a circular thing. It is a spiral. So you keep on going, right? So it's about reusable prototype with business analyst and the customer reviewing the current iteration and providing feedback to the development team. So that means you build something called the prototype, show it to the customer, and the customer gives some feedback, and then you improve it, right? And then you go back to the customer. So there is also joint development where you build something, go show it to the customer, get the feedback, and then make the changes, right? Now, this is mostly suitable when it comes to GUI-based system because customer doesn't understand your algorithm in the sense like they will not be able to go detailed to it, but they can give you feedback on your GUI. So Spiral is okay when you have like a heavily engineering GUI project, right? So, but if you have a lot of algorithmic based things, this might not be suitable. But there are also a few variations. One is RAD, Rapid Application Development, which was actually possible with Visual Basic, where you drag and drop the component to the screen, write few code, and then when the customer sees it, they see the interface, they see the UI. So the giving of the feedback is very simple. And then similar to that, we have another one called the Joint Application Development or JAT model, where you work with the client sitting next to you, and then, or maybe two programmers working together. It's called extreme programming. Either way, so there is more than one person to work with the other person, and things can run faster because there are two people, two brains working together. And then we have the dynamic system development method or the DSDM model, where things are changing. So because things are changing, we also keep changing the model, right? Now, we will see our third one is on agile. Looks like it's very similar there, but there are some changes as well here. So as you can see, here we have the prototype one, right? Concept requirement, concept of operation, requirement plan, requirement verification, development. And then we have the prototype one. And then it goes on with the rest of the things, verification, test plan, and again we come to prototype two. And again it goes on prototype three. And then you go detailed design, code, integration, all that coming. So it's a never-ending cycle here, the spider. Next one is also a very, very important one. This is called the rational unified process. There's a nice story behind a RUP model. Three different top-class software engineers, James Rumbo, Grady Booch, and Ivor Jacobson. These three people were developing separately, on three different lines. And at one point, they come together. And then they developed the rational unified process. And these three were known as the three amigos, right? Or three friends in Hispanic. So RUP is very famous in the 80s and the 90s also. So here we are looking at the users. So we start from the user and say, right, okay, who is the user? What does he want to do? Right? And let him explain what he wants. So it's called the use case scenario. Right? And then with the users, we develop the architecture of the system as well. And then we can also look at iteration and incremental, meaning we understand the whole picture, but we go steps at a time. So we take a simple section, we complete that, we go to the next section, and next section, right? So there are cycles, there are phases, there are workflows, then there is risk mitigation, quality control, project management, and also the configuration management. All these things are coming under the RUP mechanism. Now, for RUP can be used for both simple projects to complex project, right? Why this is very famous was when you start the project, actually in the actual world, all requirements are not clear, right? All the requirements are not clear. So they may be different from one client to another client, right? So we need a dynamic mechanism to make sure our understanding of the system is good. And this is also a way to reduce risk, right? And the tool also has visual things. This can be used for specification development, even designing of the software, right? So it's a very interesting one, and it was gathered very well by many people because it was such an interesting way to develop software. Now, here's a chart showing you multiple phases of the rational unified process. So starting from, let's say here, this is the discipline. So there is inception, that is the starting of the project. Elaboration is where you expand the understanding of the problem. The construction is where you do the development. Transition is where you complete the code and maybe give it to the customer or something, right? So that can be again broken down. Now the thickness here or the height of the here is about the complexity. So business modeling is happening here. So there's a lot of work to do in the inception stage, but it sort of die down when it comes to transition. But it is still there, you see. Little bit of work is still there. Requirement, again, there's a lot of work happening during the inception and elaboration, but it comes down eventually. Analyze and design comes after the inception, but it starts somewhere here, but most of the work is happening during the elaboration, and then it goes sort of down here as well. Now, you can see certain things are coming up and down during construction, right? That is because when we start coding, we realize certain issues or problems or something like that, which we can fix here. That's why it is still there even in the construction phase. Implementation is happening under elaboration, and then a lot of work is going on under the construction phase. Test and deployment happening, maybe little bit of testing is going on, but most of the work is happening towards the end of the construction, right? And deployment is like finishing and giving it to the client. That happens way towards the construction phase. And configuration management is about the deployment system, as well as if you are using modular system, those ones. So the configuration of the whole thing also goes through a massive change and a lot of work going on under the construction phase, plus also in the transition phase. If you look at project management, they are very heavily used, right? Very heavily used throughout. Environment is about development environment here. Again, heavily used throughout. Every time the pace is changing, there is a coming up here, right? So we can actually break each one into multiple tasks as well. So multiple, we call it iterations. So for example, elaboration might have 3 iterations. Construction might have, let's say, 5 iterations, meaning you build something, a prototype, you give it to the testing department. They do that, come back to you. Then you release the next version. So each version can be an iteration. So like this here, right? Inception, elaboration, construction, transition, and production. You can see they are all interconnected as well. And this is known as the rational unified process. Okay, here's another way to look at it. So inception, you need to do a lot of communication with the customer. And then through that, you do a lot of planning. And with the planning, you do a lot of modeling. That's the elaboration, right? And then you start building and releasing. Build, test, release. Build, test, release. And then once that is satisfied, we go to production and then, of course, feedback. Right, that's another way to look at it. Right, so our last one, which we will be using throughout our unit this time, is called the Agile methodology. It's very lightweight and also very responsive to the customer, unlike group or other mechanism that we discussed so far. So here, the whole reason for Agile is, if you take waterfall method, in the real world, you will never get a perfect waterfall. While you are halfway into something, the customer come back and say, look, I want to change, right? So everything that you build so far will be wasted. So in Agile development, now look at the numbers here. In the waterfall model, halfway through the project, 100% of the requirement are typically 50% done. Do you understand? In the waterfall method, 100% of the requirements are only half done. You have another half to do of the requirements, right? Now, what if the requirement change? That's another big problem. We don't know whether requirements can change, but in the real world, yes, the requirements are also changing. Whereas in the agile development, 50% of the requirements are typically 100% completed halfway through the project. Now, what does that mean? In agile development, your requirements, 50% of the requirements are fully complete. Code done, tested, of everything. So then it's a matter of doing multiple circles, isn't it? To complete the agile, through agile methodology, in order to complete your project, it's just multiple circles. That's all you need. All right. So this method has a strong collaborative style of working, unlike the other one where you work with the bigger team together to complete the project. So this is why Agile is very famous now. By the way, Scrum is one. So we will be looking at different ways of using Agile later. So don't get confused with the Scrum and the Agile. Scrum is just one method. Okay. So how does it work then? You start with, let's say, defining what we need to do. And then you design it and you develop it. You demo it to the client, and the client will say, yes, we can release it. If the client is say, no, I want some changes, no problem. You bring the again to define, design, develop, demo. Until the client says yes, you keep on doing that. Right? It looks simple, but it's actually very, very effective. Because if you look at some of the projects we have these days, the customer doesn't understand the full requirement. They don't know. Yeah. And because they don't know, we shouldn't be building the whole thing at once. We should pick few things and we build it, and then we show it to the client. And when the client says, fine, I understand. Okay, then we go to the next one. Right? So feedback and adaptation is very, very frequently done. So here we are basically building something called the user stories, and we also have something called sprints. Right? I will also share with you a free tutorial from Coursera. Just, I think it's a couple of hours project. You can go through that. That will give you a very good introduction to all the jargon that we will be using on Agile. Because if you are joining an organization in your, at least for your final year, you must know the jargon of Agile, because they will say, look, we are bringing you to a sprint here. You must know what is a sprint. Okay. Or they'll say storyboard. So you should understand what is a storyboard, right? Story points. What is a story point? Yeah. So things like that. And then it's also very iterative and incremental process. And then the whole project is divided into iterations, and each iteration generally in Sri Lanka, it's about 2 weeks, right? It's called time boxing. So we use about 2 weeks of iteration, or sprint is 2 weeks. So we work for 2 weeks, nobody is disturbing you. After 2 weeks, you come and demonstrate what you have done, and then you go to the next level, right? Next 2 weeks. So all the changes and updates that you receive for the first 2 weeks of work can be taken to the next 2 weeks of work. And last point is very, very important. Delivery is made early as possible. So your job is to deliver as fast as possible. Right? So within that agile process, we are looking at maintenance. We are looking at building and delivering as very, very important items. Now, we also have another word called refactoring and evolutionary design. Refactoring is you write something and then you make sure it works, and then later you come back and change it or update it. That is refactor, right? And now in the later style, we also talk about something called the continuous integration and continuous delivery. There are two things coming on. CI/CD it's called. And there are new terms like DevOps, where CI/CD is very heavily incorporated into companies' software development cycles. So the emphasis is on quality. There are also something called stand-up meetings, where every day morning, let's say 8 to 8:30, very short time, not hours, 8 to 8:30, there are meetings, short meetings between teams or within the team, actually, right? And they talk about, okay, what happened yesterday and what is the plan for today? What are the issues they face? How can we solve it? For today, only one day they discuss, not for the next 1 month or week or whatever. What can we do today? That's all we talk. Right? And direct interaction with the person, right? So one-to-one. So that way we can solve any issue very rapidly. All right. And then decision making is done very early. So the agile approach is very flexible and very dynamic also. And that's what many organizations use these days. Right? And there are lots of things. Now, one very famous method is called the pair programming. Pair programming is where there are two people working, and the style of working is where like two heads are better than one head, right? So maybe both people are working on the same code. There may be practical issues like, okay, how do we commit the code? But then it probably someone might be doing the code and the other person may be doing code review. Or next time, tomorrow, the other person is coding, this person is doing code review. So that way you don't clash the code, but both of them are putting their heads together to make a better code, right? And one of the biggest point here is automated testing. So there is unit testing, acceptance testing, performance testing, and also integration testing. And there are also separate builds. So there is something called the staging, delivery, and production build, stuff like that. So we'll be talking all about it later. We'll be doing some sample. And you can, when you have that multiple builds, you can also automate it, right? So you can program your system to automate the build and run on the test server. And only if it is successful, you will release it to the production server. Otherwise, if you release it directly to the production server, and if there are any bugs that was introduced along the way, it might crash the entire system, right? So there are other concepts like TDD, test-driven development, right? Or DDD, domain-based design, right? So there are lots of different ways of doing the agile. We will get down to some sample and see how we can actually use these techniques in the real world. Okay, so the whole exercise of this unit is to make sure you are ready to go and tackle these things in the industry. So you should be able to know when you go and join a company, what you're talking about, what they are talking about, and how can you join directly into the ongoing affairs of the organization. Plus, the techniques you'll be learning here, in fact, you must use it in your final year project, right? For example, are we going to use Bitbucket or GitHub, right? So GitHub is fine, but when it comes to Agile Scrum development, it's very bad. It doesn't have much support. Whereas if you use Jira, which is the tool used by many software development companies, a lot of tools are there. Like Jira boards are there, Agile boards are there. You can have burn rate calculation. Everything is integrated, right? So before you join the industry, you should have used all these tools. So stay with me. I'll be taking you through these steps and show you how to build software using the industrial strength tools that are used by the industry today. Okay. Well, I guess that's all for me today. Any questions?